Hi everyone, my name is Noam Abadi. I'm doing my PhD at the Department for Integrated Research on Energy, Environment, and Society of the University of Groningen in the Netherlands. And today I'd like to tell you a little bit about my work on dynamic networks from the perspective of maximum entropy. So in the department, we studied lots of different systems from energetic grids that satisfy sort of the needs and wants of society, how cultural, societal, and political aspects influence these requirements, and what are the effects that these have on ecological systems, on the environment. And a recurring theme in all these studies is to study these systems as complex networks. So essentially, it's a little bit surprising to find that there's a single way to think about all these different systems from the point of view of the same framework. And the reason that this seems to work is that networks are essentially a way to think not about the specific details of how the interactions might work, but about the topology in the sense of who affects who in the system. So how do networks actually achieve this? A network is essentially a set of components represented by nodes, and the interactions between these components, which are called links. So depending on what kind of description we might want to do, then we can have networks where the links are either on or off, or we can have weighted networks where we have a certain sort of flow in the connection. And the way we represent these is by what's called an adjacency matrix, which is essentially a matrix in which the rows and columns of the matrix represent each of these nodes, each of the components in the system, and the entry of the adjacency matrix is the sort of intensity of the interaction between them. So, for example, for the case where the connections are either on or off, then the elements of the matrix are binary, they're zeros and ones. If the connections have a certain direction, so A only affects B without B affecting A, then we have if the connections are undirected, so A affects B and B affects A, then we have a symmetric matrix, and we can add the weights by using real numbers or integers in the entries. So as I said before, what we want to do is construct a perspective on the dynamics of these objects, and we want to do it from the statistical point of view of entropy. So before we get into that, I'd like to give a quick overview of what entropy is and how it's used. So essentially, the concept of Shannon entropy, what it tells us is that if we have a distribution on some random variable, which we are interested in, but we don't know its specific shape, but we do have access to some properties of the distribution, some average value, then we can make a sort of best guess of what the distribution might look like by maximizing what's known as the Shannon entropy of the distribution subject to what we have measured. This is done by constructing a Lagrangian and imposing the measured values.
So, but you don't know what fnx is?
No, we don't know what rho of x is. We do know what fn. Yes, fn is a certain property. So, for example, if fn of x is the identity is equal to x, then essentially we're measuring the average value of the distribution. So we have the mean value, and we just don't know what the shape of the distribution is. And so essentially what Shannon tells us is that if we maximize this Lagrangian subject to what we know, then we are able to guess the shape of the distribution in a sort of optimal way. And this gives a pretty general result on the functional form of the distribution based on what specific property we are measuring. So for example, if we only know that the distribution has a certain mean value, and of course that the distribution is normalized, then we get an exponential distribution because the functions that we're choosing are the constant function 1 and the identity x equals f. If we also know, for example, the second moment of the distribution, then we'll have an additional term inside the exponential, which turns our distribution into a Gaussian. For a third case in which we also know the first and second moments of the distribution, but we also know that they have different values, and the shape is still a Gaussian, but the parameters of the distribution will be different. So how does this apply to complex networks? Well, essentially, since the network can be thought of as the adjacency matrix, then essentially the sort of inference we're doing on the distribution is on the state of specific links of specific pairs of nodes between the states of specific links in between each of the pair of nodes in the network.
If you need it, there is a stick.
So essentially, we're taking the state of each connection between each pair of nodes in the network. And what changes from the previous case is essentially how we impose the constraints on the system. So now, instead of having the state over the whole single distribution, then we have a normalization for each pair of nodes in the system, which essentially is saying that each pair of nodes in the system must be in one of the possible states. And this is a link-specific constraint, which almost always will be there. And we can also add other constraints, for example, on individual nodes. So here we have a constraint which represents sort of the total intensity of connections coming from a node I. And here we have the total number of links, or the total intensity of the links in the network. So we see that we can specify constraints on different scales of the network. And this method has lots of applications in understanding complex networks as objects to understand widely different systems. So, for example, we can use it to understand why certain properties give rise to are related, to certain others. We can use them to guess where links are in the network, or use it to identify communities in different ways according to what information we have. And all this is really nice, but since the concept of Shannon entropy is specific to static distributions, then it doesn't give us much view on the dynamics of this network. And the dynamics of the networks are actually interesting because all the systems that I mentioned before are actually dynamic systems. So, for example, energy grids are constantly being restructured and upgraded. Ecological networks are composed of nodes which kill and give birth to each other, and social networks are composed of people in which essentially sometimes talk and sometimes don't to each other. So having a perspective on the dynamics would be really useful. And that's what I want to show you today, how I think we can do. It's not that there aren't any perspectives on dynamics on complex networks. So, for example, the Watt-Strogatz rewiring process is one of the most widely used models in complex networks. And essentially what you do in this process is you start out with some usually regular network ordered, and you choose links at random and essentially place them between different pairs of nodes which were initially disconnected. So as you repeat this rewiring process, then you end up at a sort of completely disordered state of the network where any pair of nodes in the network, it can be connected with essentially the same probability. This final sort of extremely disordered case also corresponds to a maximum entropy network, which is defined by one of the constraints that I showed you before, which is essentially given by having the same number of links that it had in the beginning as it does in the end. And so essentially we're saying that the state in the end is one where you take this initial links that you had and you just distribute them evenly between all the links you have in the network. So if we're able to reconstruct a dynamic perspective of this process, then we can think about this final state as a sort of equilibrium distribution on the network, just as we can think about the equilibrium distribution of Maxwell-Boltzmann as a relaxation to equilibrium of interacting particles. So how do we do this? Well, essentially, the proposal is that instead of thinking of the state of a single link at a specific time in the network, we think about the history, the whole evolution, and take that as a random variable. So if our previous state was, for example, on or off, then the whole history will now be that the link is, for example, on, off, or on, off. We consider this as a random variable, and we calculate the Shannon entropy of that distribution. Then the constraint that we usually have is the constraint of normalization of the distribution is replaced by the constraint of marginalization. So essentially what we want from this is that instead of saying that that we're talking about the whole evolution, we want to think about the process. We want to think about how the history is updated when we have a new time set. So this can be thought of as sort of freeing us from the responsibility of what the history of the states is, and only letting us sort of conserve this normalization instead of on the whole distribution. In the same spirit, since we're thinking that the rewiring process is essentially conserving any initial nodes in the network, then we want it to conserve this number of links. We don't want it to have any specific number. And so we can write the constraint for that in this way. And then finally, we need an additional constraint, which is that when we measure two successive time states, two successive states of the network, then we want there to be some difference. So essentially, we're taking the link from one place, placing it somewhere else, and there has to be some difference when we measure those two successive states. So these compose our constraints on the system, and from here, everything is pretty much the same as it was before. So we construct our Lagrangian, which is based on the Shannon entropy of now the full history of each pair of nodes, impose the constraint of marginalization, and then the two constraints of essentially the time scale, the difference between two states, and the number of nodes being constrained. We maximize this Lagrangian, and we find a functional form for the distribution, in which it's already interesting to note that the whole dependence on all the history that we have before is only here in this term. Everything else is just on the state that we want to know how is updated and the previous state. And this doesn't depend on which specific pairs of links we're looking at in the distribution.
No.
So,
Question.
yeah.
Does any of these is equivalent to the fact that the process is Markovian, or that's independent?
I'm not assuming that the process is Markovian.
So the second one is the conservation of the degree.
The second one is the conservation, no, of the total number of links.
The total number of
Yes. Yeah, that's actually for the next slide. So sorry. Yes, so we see that the dependence on this whole history that we have not imposed as something specific is in this term. So now we want to go ahead and impose these constraints that we have before, in particular the constraint of marginalization. And when we do that, we see that the whole dependence on this updated state that we're interested in, that is what the new state in the network will be, is completely independent on, again, which specific link we're looking at. And we see that the whole history is in this term here. So we can define a transition matrix of our new state given the history, which is dependent only on the state that we're updating and the previous state. So as you asked, the fact that the process that we have here is Markovian actually emerges from the constraints that we impose, not from any specific other requirements. We also see that the transition from the previous state to the new one is independent of the specific links the specific link we're looking at, and that's a consequence of the constraints being global, that on the whole network. So this defines essentially a transition matrix of essentially from having a node in a link in a certain state to the updated states, which essentially defines a creation probability and annihilation probabilities for this network. And this is a transition matrix also in the sense that the columns each sum up to one, conserving the norm of the probability distribution. And again, that's all a consequence only of the constraints that we imposed. Also, when we impose the other two constraints that we required, we see that the creation and annihilation probabilities for each of these links, that is the probability of going from 1 to 0 and 0 to 1, are essentially a uniform probability among the connected or disconnected links. And so this again is reminiscent of the Watts-Strogatz rewiring process, but are they in fact the same? So in order to test this, what we're going to do is we're going to start with an initial probability distribution for the whole links. We're going to take a certain sample. That is, we're going to sample a network from this probability, and we're going to carry out the Watts-Strogatz rewiring process from this initial sample, essentially recording the whole history. And at each time, we're going to get from this the probability of finding a specific link ij connected. So this, of course, is computationally, for example, intensive process because we have to do many realizations, which depend on the size of the network, depends on what precision we want to have on the initial conditions. And our other method is essentially taking the same initial condition that we had before, applying the creation probability and annihilation probabilities to get an analytical evolution, and that's that. So it's pretty much a simple process. And when the initial conditions that I'm going to show you are the ones shown here. So each of these essentially is a heat map of the probability of finding links between each of these pairs of nodes, and below you have some samples of what these networks might look like. So if we take, for example, one of these samples and always use it as the same initial condition, then we can repeat the same process as before, and we can repeat it. We can use it from the point of view of the transition matrix and compare those two evolutions. And effectively, we see that
Wait.
See.
Go back.
Yeah.
So the initial conditions are probabilistic. The colors are probabilities that the corresponding nodes are connected or not, according to the color.
Yes. Yes.
Okay.
So blue is 0, yellow is 1. So for example, you have a regular grid in which the links are essentially deterministic.
That one is deterministic, but
yes.
The other ones are random.
The other ones are random. So you'll never see, because the connections between the small block and the large block here are always 0. You'll never see connections here, but the connections in here will be random.
And you will be using all of them or any initial conditions.
I'm gonna. So what I'm showing in the next slide is always using, for example, this one, this one, this one, this one, each of the images. Okay. And then we're going to look at when we take more samples. So, for example, here you see that if we look at a specific pair of nodes, some of them start out with probability 1 because it's a deterministic initial condition. And we look at the evolution over time, comparing the realizations and the evolution according to the transition matrix, and they both match pretty well. So for example, in the Mediterranean here case, you see that the distribution is a bit more noisy because I've used less samples, but here we have more samples, a bigger network, and the curves seem to match better. Then we can also do the same for pulling out many different samples of from the same initial condition. And then we actually see that sometimes the links are on, sometimes they're off, and on average they have a certain value. And again, the process matches. What degree distribution? So it depends on the initial condition. For example, in the configuration model, what I did was choose I sampled the Lagrange multipliers for the configuration model uniformly and just constructed the configuration model from there. So it's just to get some initial condition and to see that for different initial conditions there, it also works. Yes. So, for example, in the case of the Erdős-Rényi network, then when we take multiple realizations, of course, because the Erdős-Rényi network is the final state that we expect to find, then we don't see any change except for some small variation at the beginning because of sample size. For the other cases which don't correspond to the equilibrium case, then we do see that there is a relaxation into this uniform probability. So each of these lines here is essentially looking at one pair of nodes and looking at how the probability of finding a link there evolves over time, pairing the evolution to maximum entropy and from the simulation.
And how big are the networks? The ones that you use?
So, for example, the Erdős-Rényi network is just 10 nodes. The regular grade is 30, 40, and 100.
And you said that the thing is that that's computationally intense to measure the.
Yeah. So, if I wanted to do, for example, if I wanted to do a network of thousands of nodes, then I need to do a lot of realizations, a lot of samples, and I don't really want to do that.
The curves, the black curves that you have in the following one, those are just the analytical expression.
Yes, they're the analytical expression from here. So essentially, from the transition matrix that we find here, that the creation and annihilation probabilities of the links can be used because we have only two states. Then we can use this to essentially look at only the probability of the link existing. But if it were a weighted network, then we'd have several different states possible, and we'd have to do it slightly differently, but it's the same idea. So we use these creation and annihilation probabilities to look at the evolution from these two different points of view, and they match. So we can skip this whole sampling process and just go to the analytical evolution based only on the constraints that the process obeys. Okay, so I hope to have convinced you that we can use this to essentially skip this whole sampling process, that the processes are equivalent, but can we do something else, something beyond just the conservation of the number of links? In particular, I said before that when we have the same functional form for the constraints, the same fn, but we change the value, then the only thing that should change is specific parameters, but the functional form of the results that we get here should be the same. So in particular, if we take the constraint that was for the conservation of the number of links, and instead of saying that the number of links is conserved, then we say that there's a certain number of links that are created and a certain number of links which are destroyed, then the difference between those states can be non-zero, and then we're just saying how much the number of links changes. And when we look at the difference between two states of the network, so essentially we look at the two separate time steps, and instead of having just two changes between the two states, then we also have the links which are added and the links which are removed. Then it's also written in terms of those parameters, and we can make these parameters be anything we want as long as they make sense in terms of the network. So we have a place to add 50 links in the network, then we can't add 100 links because that just doesn't make sense for the initial conditions. But in general, we just say, okay, there are a certain amount of links which are added and removed that evolves over time according to whatever I want, and we see if this matches some sort of rewiring process. And the process that, since we're changing the number of links, then the corresponding simulated process would be one where essentially we're saying, okay, so besides the two links that we're changing, then we're gonna add this amount of links. So choose a certain amount of disconnected nodes, add delta C. We choose a certain amount of connected nodes and remove delta A. And we do the same simulation as before, so comparing the two different the results from maximum entropy and from the simulations. And again, we can see that, for example, if we impose that the difference between delta C and delta A gives us a linear increase in the number of links, so this is just using the same delta C minus delta A at each time, then this also matches the rewiring process, and the maximum entropy results also match. And again, we have a creation and annihilation probabilities, which are essentially uniformly distributed among the existing and non-existing links in the network. We can also make this average number of links oscillating time. So again, this is choosing delta C and delta A however I want in order to get a certain oscillation. But it would be, for example, more interesting to get these delta C and delta A from some other conditions. So for example, I could make it logistic and model, for example, the filling of the network. But the idea of looking at this from this point of view is that essentially we can find many different processes in which these constraints hold, and that the difference between the rewiring process and the maximum entropy results match again. So to conclude, I've shown you that we can construct a maximum entropy perspective on dynamic networks, which essentially agrees with the known process of what's Strogat's rewiring, in the sense that they are two processes which have the same constraints, one from maximum entropy and one just from how we understand the process. And we can also take these processes and change the average values in the same sense that we can change them from the point of view of maximum entropy, and still get a sort of process that agrees with what we would expect. As future work, I think there's much more to be done that has been done. So for example, we could think about what happens when the process is updated continuously, or when the links have continuous or directly weighted networks. It's also interesting to think about what happens when we vary the number of nodes. So essentially, this is always kind of problematic from the point of view of entropy, because essentially the Gibbs paradox happens. If we want to actually think about dynamic networks, for example, ecological networks where the components are changing, then this will be needed. Next is thinking about non-Markov process. So maybe we can impose constraints where the difference, the constraints actually don't end up with a dependence only on two successive time steps, and maybe there will be something interesting to say there. And finally, for example, simultaneous optimization, because essentially we're assuming that this process emerges from maximizing the entropy. But if we think about, for example, evolution, ecological networks, which are subject to dynamics from evolution, then we'd also want there to be some other target functions, fitness or something like that, that should be simultaneously optimized with the network. So thank you. And
Question.
Go back to where you have the explicit form of the constraints. Of this one. Stop there. No.
This one?
That, so you have these constraints, and this correspond to a certain dynamic on the net, which is switching on or off the links.
Yeah.
Right? Is it true? It's a question. That if you put other constraints, I don't know, powers, this or there, any function, there would be a dynamic that you could find or not, easily or not, that would correspond to that choice of the constraints.
I think that's, well, that's why I said, for example, for the Markov and non-Markov process, because you could, I think you should be able to impose any function of the whole history, for example, and then the optimization would lead to something that depends not only on two successive states. So I think it would, but I don't know. I'm also not sure mathematically like what exact requirements are needed for this to hold.
Just curious about for the ecological network, what does it mean to have conservation of the numbers?
So it depends on what your network represents, of course. But for example, if your ecological network is essentially predator-prey relation, so you have certain species, A consumes B, B consumes C, C consumes D, then essentially the rewiring would be like saying that you're changing the relation between who eats who. As time goes on, then maybe one species evolves in order to be able to not be consumed by some other, but in place taking another. So conservation of links in that case wouldn't be a very adequate choice, I think. But I think like as a starting point to see if we can actually do this from the dynamic point of view, then this was my proposal.
Does it have just to constrain the number of links and change, so you say, think, or you've observed the number of links has altered?
Don't alter.
So I guess, so if you conserve the number of links, species A eats species B, you move that link, then you're imposing that to other species. Automatically, species C starts between but how does that make sense? Because there's
no. That's why I say that for ecological networks, I'm not sure if these would be the adequate constraints to simulate this. But
so would this constraint, the new constraint that you have here, with the difference, would that help or that?
Well, that helps a little bit because then we're allowed to do whatever we want with the dynamics of the network. But since this, so for example, here you see that as time goes on, this eventually converges to essentially all the links having the same probability, which just fluctuates over time. So you're looking at the sort of equilibrium case where the links are uniformly distributed and you're just changing the level at which this is distributed. So it gives you some more freedom to what your system looks like. But for the ecological networks, I think it would be much more sensible to think about other constraints, for example, on specific nodes, on specific links. And I actually did the calculation for that case, and you get a creation and annihilation probability, which depends on your specific pair of nodes. And because that happens, then it's much more difficult to actually find what that probability is analytically. So it just becomes a much more difficult problem to deal with in that case.
For logical network, most of you have already the logical network that is coding some information disconnected to the different relationships that are between different species. And you want to know how this network can change, preserving the structure of the network, preserving the links of the network, but just supposing that the links will be traced randomly. So you want a sort of fluid model, a random network with the same structure of the real network. And for that, as a human model, and see whether information that is coded in this random network is the same as the information that is coded in the real. And for that, maybe what you can do is just randomize the links, interchange the links, and perhaps trying to get some information about the real system to compare with a random system with a similar structure. But it's the same, but similar in the sense that we have the same.
Or would you do that? Then you just have a static maximum entropy.
Yeah.
But essentially, in that case, what you're asking from this point of view is how does it relax to that extent?
Supposed to become something things or nodes that are in the universe, and they are the sort of logical system that stands for the different nodes, and they trace links according to the state of the node. How straightforward is from this dynamic to build up the constraints?
I think that the general problem is essentially that instead of having a function here f of x, like you have a function which depends on the specific node that you're looking at, right? So, for example, if it were a fitness, then so, for example, you can take this constraint is the total intensity of connections from one link to another. So if this represents the predator-prey system, then essentially what you're saying is what the total number of preys of the system are. So you can go ahead and modify this function here, use it as fi, for example, fj, which tells you a sort of relation between the fitness of the two species, for example. But then you usually run into the problem that the result is dependent on the specific pair of nodes, and then it becomes difficult to calculate that analytically. But you can get a functional form, which is at least a start.
Any guess? Okay, thanks.